Hi, my name is Honggyu Kim, and I'm working at LG Electronics. And the title of this topic is understanding the runtime behaviors of C++ programs using uftrace tool. I did the Lightning talk last year, and then I'm doing the same tool, but I'll be more focusing on the analyzing the C++ programs this time. But at the beginning, I'll show you the basics first. Okay, uftrace is an open source tracing tool, and then you can download it from GitHub. Yeah, and uftrace is created by Honggyu Kim, and then he's one of the active developers of Linux perf profiling tool. So this tool is just like a perf-like USG. So at first you have to record all the function trace, and then you can analyze it using the replay command or report command, those kind of things. And uftrace is able to trace C or C++ user space programs and library functions and Linux kernel functions inside as well, and some of the system events. But I'll be more focusing on just user space programs and library functions. So first, function tracing is just like if there is a source code like that, and the main function calls foo and foo calls bar, and you can just compile it, and you get this kind of binary. But if you recompile it with -pg option, and it inserts all mcount function calls at the entry of each function, and uftrace uses this mcount function calls. And after compiling, you can just execute it. But if you put a uftrace record at the beginning, you can trace all the function traces. And you can replay it. Or just you can just do the live command. It's just a record plus replay. Because that the default command is live, and then you don't have to put it. This is a call chain, this is a thread ID, and this is a function execution time for each function call chains. So, and if I put a library function calls in bar function, you can also trace it. So in the bar, there is another function called getPID, but at the end there is a PLT symbol. It means that it is not calling the function inside the binary, and then it is going outside of the binary. So there's a kind of table, and then uftrace just hook the table to trace the library. In that case, you don't have to recompile your program with -pg option. Library can be just traced without problem. But if you recompile with your program with -pg option, you can also see the user space functions as well in this way. And it can also trace the multiple processes as well, just like there's a fork and wait and getPID, those kind of things. And then if you see, and then there are two different thread IDs. And Linux, you can also trace the Linux kernel functions. You need to have a root privilege, and then if you put -k option, you can see the output like this way. And then in printf, there is a do page fault and flush, and then there is a system call, syswrite. The next one is the event tracing. I'll just make it very simple. There are many different type of events, but if you put -e and Linux schedule, you can trace all the scheduling events. It doesn't require the root privilege, and then you can read it from the user space. And I'll introduce the filters. Okay, if you put a -d2, it limits the depths of the function calls. And if you put a -f foo, you will just filter only foo functions and its children. And if you can just hide some specific functions using -n. This way you can hide it. Or this is a time filter, and this because in a big program, there are too many small functions. You can just remove all the small functions using this way. You can just put a time threshold, and then under the time threshold, all the function traces are just disappears. You can save a lot of data size as well using this one. And report. And after compiling it, recording, and you can use a report command. It shows just a summary, the entire execution summary. And at first, and then this is by default sorted based on the total time. But if you want to change it, you can sort it based on the self time, and you can sort it as a call time, number of calls. The next one is a bit very small actually, but I just want to show you that there's another feature because uftrace can record twice, and then you can make a diff in the summary. So if you examine it, and you can see some plus minus symbols, and then this is LLVM actually, but just I'll skip it. Okay, there's a Fibonacci example I showed you before, but I'll just go very quickly. It shows like that. And then if you want to see the arguments, and then you can use this option, you can also see the return value as well. This is a kind of a formal definition of how you can specify the types. Because it doesn't require the debug information, you have to explicitly specify the type. But if you don't specify the type, it uses the default. At first, you use symbol, and then some specs, and then for arguments, and you have to specify the number of arguments, the place. And there is a format as well. You can also specify some kind of string character or std string as well. And first you record it, and then you can also dump it. And then the --chrome option just provides this kind of a JSON format. This JSON format can be opened in the Chrome browser, and if you go to this site, you can just open it in the browser. This is a built-in function in the Chrome browser, so it doesn't require any other installation. This is timeline, and this is called apps. But some of the people can just load it as a JSON format, but the better way to use it is to translate it into HTML file. You can go to this site and then download it, and then you can just convert the JSON format to the HTML file using this way. Then you can just upload it in website, and then it's a lot easier to read. Or once you record it, and then you can make a flamegraph output as well, this way. This is different from the Chrome tracing viewer. This is not timeline based, this is just aggregated data. So the next one is we can also trace the pre-built binaries, because we don't trace the user space programs in that case, but by tracing some libraries, and then we can still get some useful information. So let's say there is a GCC binary. This is pre-built, and then we don't have source code, and then GCC binary is just compiling it. And then if we put it, it just shows this kind of error, because this is not compiled with the -pg or some f-instrument functions. If you put --force, you can trace the library in this way, but it shows only the first level library calls, just like an ltrace. And if you put a -t, 200 microsecond, you can see just a big picture of the execution. If you use a --auto args, this is not merged yet. This is working in progress. You can print the arguments and return values automatically, because uftrace can understand some well-known libraries. So you don't have to specify all the libraries and types. It's not necessary in that case. And you can also make it as a Chrome format. It provides some kind of information. Because at first, CC1 just translates source code into the assembly file, and AS translate the assembly file into the object format, object file, and then at last it calls the linker. And then as you can see, the linker is busy in that case. And you can also trace the nested library calls because as I mentioned, by default it traces only the first level library calls, but in that case, and then so we miss a lot of library calls. This option just follows all the library calls inside the library calls. So this is a Clang binary tracing. And then if you trace the Clang binary, you can see this kind of nested library function calls. This is also private binary. And so we can see the function trace, and then so what's good. So there are some use cases. And then there are QtQML engine, there was a bug, and then so some friend just fixed it. And then he did a lightning talk actually, so I think I'll just show you just a simple thing. And then he found some kind of buggy case, and then so there is a broken case and then working case, and then he found the difference, and then he found the exact function, and then he just fixed it. And then if you want to know more, and then you can just watch this lightning talk. And the next one is just a C++ example, the const expert function. Let's say there is this kind of example. The Fibonacci number is calculated, can be calculated at compile time because I put the const expert. But in this case can be calculated at compile time. But what do you think? This can be calculated at compile time? But if you see the function tracing, it's clearer. After compiling it, and then if you see the function trace, it just calls the Fibonacci functions at runtime. At first, the first one was calculated at compile time. But this is not the only problem. If there is a const expert, the first one was calculated at compile time, but the return type is const int, not const expert. In that case, there is some strange behavior. If you compile the same program with Clang, and then the first example is also executed at runtime. This is kind of a strange behavior between the GCC and Clang, maybe. But if you see the function trace, and then you can see it more clearly. There's another example, std string view. Let's say there is an example. Const character pointer is passed into the one function, and then the function just accepts a std string reference. In that case, if you see the function trace, there's a basic string, the constructor and destructor. If you optimize it, only just to operate a new and delete as shown here. Anyway, the memory allocation is done. So that's why the C++17 has a string view. If you pass it to the string view, it makes some basic string. It calls basic string the constructor, but if you optimize it, everything is gone. So that's why the string view is necessary in that case. So the next example is a STL container performance comparison between the vector, deque, and list. There's a benchmark like that. We can just push a lot of iterations, and the type is std string, and then we can push to the vector, and we can push it to the deque as well. And then at last, we can push it to the list. So there's a iteration counter. If you record it using these arguments, and then you can see the call graph using the graph command. The output looks just like that. It's a kind of summation, and then it shows all the call chains, and okay, as you can see, this is the execution time of each call chain. and this is the call chain, as I mentioned. And this is the number of execution, number of calls. So if you see the replay output, a lot of patterns are repeated, so you cannot see in one single screen. So the vector, as you can see, the vector spanned 2.1 seconds in that case, and then the queue spanned 700 milliseconds, and the list spanned 2.4 seconds. But the good thing is that you can see the performance difference in that case. So there are a lot of man copies in vector, and then at first vector, and then I colored it in red, it spent a lot of time here. I'll show you the difference. In the vector pushback, if you see the replay output, at first it allocates 32 bytes of buffer, and then it does a man copy because I push the hello string is 5 bytes. And if you do the pushback once again, and then it allocates us 60 bytes, and then it doubles the size, and then it copies the original memory to the new buffer, and then deallocate it. If you push it once again, and then it doubles the size, and then it copies all the original contents to the new buffer, and then it repeats over and over again. And then at the last example is the man copy called 5. This is just the pushback was success without the memory reallocation in that case, because the STD string is the size of STD string is 32 bytes. So if you see, the number of mem copies are increasing rapidly. If you go more, and then most of the calls are mem copy. In DQ case is a bit different. If you see it here, and the mem copies are kind of stable, and then there is another memory allocation here. Because DQ is the data structure of DQ is a bit different. And then if the one buffer is full, they allocate a new chunk of memory, and then they allocate it. They don't copy the original contents to the new buffer. That's why they can save a lot of mem copy here. And their pattern is quite stable, and then it's the same. That's why they can save a lot of time compared to vector in that case. In list, whenever the pushback happens, and then they have to allocate 48 bytes of memory, including the pointers, and they copy it. And then, as you can see, the number of mallocs is the same as the iteration number. That's the problem. But I will just show you another example. I push it just an integer, just instead of string. In that case, it's a bit different, because if you see the call graph, integer is just it's just trivially copyable, so it doesn't have to just call main copy over and over again. It can just call just one single main move when they are copying the original contents to the new buffer. Just main move is enough. That's why the performance difference is not that high in that case. Okay, the next example is in C++17 there is a parallel algorithm. So I just downloaded the recent G++, and then there is a sort algorithm, parallel sort algorithm. So you can just execute this example. It's based on the OpenMP. You can see this kind of output. As I mentioned, this is timeline, this is a call depth, and these are the different threads. So as you can see, maybe you can get some ideas how each threads are interacted in that case. Maybe, okay. All right, this is it's just loading. right. This is the Chrome trace. You can just zoom in that case. You can zoom out. You can see the multiple threads in that case, this way. I executed this algorithm in some machine which has 40 cores. That's why it has a lot of threads. You can get some ideas by just seeing this kind of chart. Okay, the next one is that we recently added the Python scripting feature. So now uftrace is able to run some Python script. So whenever the function is entered, and then you can run some specific Python script, or whenever the function is returned, and then you can also run it. But to reduce the performance overhead, and then in Python script there is the data, and then you can list up some of the functions you specify. Whenever these specified functions are executed, the Python scripts are invoked. Except that, and then it doesn't call the Python script. It's called the function filter. And script can be executed during record time. And in that case, and then you can get some more data, you can read some kind of systems tests or something like that. But it hurts the original performance, so it's a bit slow, and then that's why we recommend to use it for the recorded data. So there's a separate command called the uftrace script. You can use this command to read the recorded data, and then you can also process function entry and exit in the same way. It provides four functions, and uftrace entry is invoked whenever the function is entered. uftrace exit is invoked whenever the function is exited, and then begin and end, those are executed only once. There is a simple example. Count variable is initialized as 0, and then whenever the function is entered, and then we increment and then when the program is exited, and then we print the count. We can count the number of function calls. So if there is a very simple example, it can be the call trace is just looks like that. If you use this command uftrace minus capital S, and then you can pass the Python script here, and then the execution flows are just like that. And then at first the Python script uftrace begins executed, and main function is executed, and main function is entered. That's why the Python script uftrace entry is executed, and foo, and uftrace entry, bar, uftrace entry, and bar is returned anyway. So uftrace exit is executed this way. It comes over and over again, and then finally it calls a uftrace end. It works like that. Then you can print the 3. In here, uftrace entry and exit accepts arguments. So the arguments can contain those kind of information: thread ID and call depth, timestamp, and function execution time, and address, and symbol name, and some specific arguments and return values. So there's another example. I just traced just a previous binary node.js, and I passed one single Python script. In the Python script, there are some kind of comments in uftrace option in here, and then so we can write some kind of uftrace record options. In that case, and then you don't have to explicitly specify the options outside. You can specify in some of the informations inside the script. In that case, you can draw this kind of chart using the matplotlib. Maybe this is just a malloc and free, those kind of example, but the good thing is that you can use your own functions in that case, and then just hooking malloc and free is a kind of a very common technique. So it's not that new, but you can use your own functions in that case. Okay. Thanks. And do you have any questions? Thanks. We have 5 more minutes.
So you have traces an instrumenting profiler using -pg. What does it compare to perf, which is a sampling profiler? What do you think is the advantage of the trace?
No, the perf is a systemized profiler, and then it's sampling based, and so it doesn't hurt the original target program's performance, but it's less accurate. And then it cannot count the number of calls, and then it cannot print the function argument and return values. It has those kind of restrictions.
Right. So trace is better if you want to get an accurate timeline which doesn't miss any function when you have arguments.
Yeah.
Whereas the overhead, especially for inline functions or small functions, is probably larger and you have trace.
So that's why we recommend to use the time filter and then to remove the small functions. But if there can be some small functions which is very important. In that case, you can explicitly specify some kind of triggers to pin the specific functions. In that case, and then even if the time threshold is, even if it takes a lot, just a very short time, we record the trace in that case. Please.
What kind of performance hit do you take for using uftrace?
I'm sorry?
How much of a slowdown do you get?
It depends on the number of records. If you record every single function calls, and then it's kind of slow, but we did some kind of optimization inside, and whenever the function is entered, and then we don't directly write to the file, and then we first allocate the shared memory, and then we just write the record to the shared memory first, and then in the background, uftrace program is just gathering all the memory and then write the file as a chunk. And if you use a -t option, and then you can reduce a lot of data in that case, and then slow down is not that much. If you're curious about it, and then I can just show you some kind of example. Clang is a big program, right? Clang can be traced using uftrace. Just like we can just compile hello world. In that case, uftrace is recording every single function calls in Clang. It may take some time, but I will use the time filter option. So now it's done. If I use a time filter, it's a lot less. Right. I have to make a space. In that case, I remove all the function calls that is under 1 millisecond. You can see just a big picture only, right? This is the entire execution. This way. Every function traces over 1 millisecond in that case. Okay.
So you can filter on functions, like can I filter on namespace?
Yeah, it understands the regex, so you can just put the namespace and then just a dot star. That's it. Yeah.
Would you mind to add MPI support to the tracer? Because the point when you run this MPI program is not like it's done.
I'm sorry. I cannot hear you.
Sorry, I'm going to speak louder. I would say, would you mind to support MPI programs for your tracer? Because the point when you use MPI.
MPI programs.
When one executable, one trace is created dump, all the dump are going to get override by the other program in parallel. Then generally you run the
You mean is multi-process programs, right?
Exactly, yeah.
It's separately executed multi-process programs. So we are targeting only single process programs, and then so if the single program creates some fork, and then we follow it, but basically we don't trace multiple traces at the beginning.
Would you accept patch for it?
Yeah, so we can make it Yeah, we can make it, and so we can merge it with the data. I think he said that the time is over, so maybe if you have questions, I can answer. Okay, thank you very much.